I'd like to again thank Nancy and Lynn for organizing this great event. It's really been a wonderful morning to hear about all the exciting research that's going on. And so what I'm going to do is tell you, I think Allison did a great job of giving a nice overview of a lot of projects that are going on in practice. I'm going to dive a little bit deeper and tell you about one specific result that we've gotten recently, looking at characterizing the performance of teleoperated robots with communication delays. So the reason I wanted to throw this out to you, because if anybody has any good suggestions on how to further explore it, I'd be very interested, because I think it's an interesting result. So let's see how we can get there. So I'm going to talk about teleoperation similar to what Allison did. This is controlling a device from a distance with a human in the control loop. And this work has been done in collaboration with the U.S. Army in Warren, Michigan, where they have all of their ground vehicles operations. And so they're interested in both of these scenarios that you see in this picture, where the robot goes someplace that's too dangerous for humans to go. And that the human has visual feedback coming from the robot, and they want to try to operate the robot to go around. Now, if you knew exactly what you were going to do, you could probably program the robot to go there autonomously and do the task. But in a lot of these situations, if you're not sure exactly what the task is, you need to have a human willing to make that level of decision. So, for example, you might consider that you want to drive your robot down this road in this beautiful mountain scenery, and it doesn't think it should be too bad to do that from a remote distance. But really, you don't see this kind of a picture. You see this kind of a picture, because you're looking through the soda straw of the robot's camera. And probably you don't see that picture either. You see a slightly blurred and probably time-delayed version of where you're going. So there's been lots of work over the years trying to understand what are the issues that limit the perception and manipulation in these teleoperated tasks. And you can see a bunch of them there. So what we were interested to focus on, again, coming from our sponsors in the Army, is what are the real challenges in time delay, and what's basically the limit of the performance we can achieve given the time delays we see in our systems. And knowing what the limits are the things that we can do to cost effectively address some of those limitations. So the setup that we've developed to characterize this performance in teleoperation is a typical feedback loop like you see here, where you have a mobile robot interacting with the environment. There's a user who gets feedback from the robot through sensors. In this experiment, we're only going to look at vision, but you can imagine maybe there's a haptic feedback, maybe there's some audio feedback, all those different senses that Allison mentioned. Maybe we want to know what it smells like over there. Has there been a fire? So I think all those sensors could be valuable, but for the purposes of this, and again, I'll say based on the state of the practice that they're currently using in the Army, we're just using vision as sensors. And then as input devices, you might imagine there'd be some haptic control or some fancy steering wheel, but in practice, they use gamepads. They're cheap, they're easy, soldiers know how to use them. And so that's what we're using as the input device. And I showed here these little delta signs to show all the different spaces for possible delays. And we're going to focus on the delay here from the user to the input. Although our research so far shows that it doesn't matter so much where the delay is in the loop, it's the sum of the total delays in the loop that is most important. But we're going to, again, try to simplify the situation. So this is the test that we ran. We have this little JavaScript simulation of a robot. It drives along this path, and we gave the user this first-person view, so you basically are looking through the straw, but you're just trying to drive the robot down this path. Now there's noise in the system, so if you're going down a straight path and you leave the steering straight, you're going to bump off a little bit just from some randomly generated noise, because we didn't want to make it too easy. And when you have to go around those corners, you can't push the stick either all the way to the left or all the way to the right. It won't be the right radius. So you need to sort of adjust your steering. And the speed is fixed, so we speed at, I think 1 meter per second, but you can scale to whatever. And we give the users a score based on how far away they are from the center of the line. So if they perfectly follow the white line down the center, they get a score of 1. If they're totally off the path, they get a score of 0, and then it scales in between. So we did this test with a bunch of undergraduates. Actually, I think there were some graduate students too, but engineering students are pretty good. And they're actually reasonable models for soldiers. They're the right age group, they have the right experience in playing video games, and things like that. And we paid them to do this task, and then we promised them, if they were one of the best performers, they'd get a bonus. Because we didn't want them to get bored and just not even try. We wanted to give them some incentive to try. And then we have this study design. But what I want you to see in the bottom is there's 6 different latency types that we studied. Because really what we were interested in, how does the delay affect the user's performance? So there's 4 different constant delays, those are given in milliseconds, and 2 different variable delays with different means and variances, where the 2 variable delays had expected values that would match the constant delays. Now, research had shown before that with the same mean value, the variable delay will have worse performance than the constant delay. The subjects can kind of learn what the delay is going to be and compensate for that a little bit. And so these are the results. The highlights in yellow just shows which factors affected the performance. Not surprising. We did this at actually 2 different speeds, so you can see the red and the blue. But so those, on the latency type, you see the 4 constant delays. As the delay increases, the performance decreases as expected. And the 2 variable delays, E and F, and for the same average value, the performance is worse with the variable delay than with the constant delay. Again, nothing surprising. And we also surveyed the subjects on how did they feel about the delay on this Likert scale, and did they feel that they could anticipate what was going to happen. So we plotted these 2 curves. So the blue is the 1 meter per second speed of the robot, and the red is the 1.5 meter per second for the robot. And you can see these are just trend lines that are fit to the median points of the data. The interesting thing that we found was when we put the variable delays back on these 2 curves, the 1 meter per second and 1.5 meter per second driving speeds of the robot fit the curve at the same, quote, equivalent constant delay. There'd be no reason to expect that they're equivalent. You should expect that the performance at the E, which has the same mean as B, should be worse, but there's no reason to expect that those should hit at the same point. Similar for the F, which was the larger mean and larger constant variance. So what's sort of cut off at the bottom there is the variable latencies fit this trend line at the same delay for both. So we had this question, is there some equivalence between this variable latency E and this constant latency of 380 milliseconds, which is kind of where it fits that line? Is there some way to look at that equivalence? And that's what I'm going to talk about towards the end here. You can also look at the subjective responses. These are, again, averages from that Likert scale. And these are the A, B, C, D. And if you try to plot these variable delays, it's not quite as strong of a conclusion that they lie on the same trend, but you would expect that they would just be in between those 2 points. So what we thought we might try to do is, can we create a model? It's expensive and time-consuming to do these kinds of experiments where you have to round up 22 students and bring them into the lab and have them sign a form and pay them $10, etc. So we thought we'd try to build a mathematical model that could behave in a similar way to a user in this particular structured task. So what you see here are 2 time series of users driving the robot around these curves for on the top with no added latency and on the bottom with the maximum value of added latency. And so the blue line shows if they're turning the little joystick all the way to the left or all the way to the right. And pretty much that's what they're doing. They're either turning it all the way to the left or all the way to the right. There's not a lot of values in between 0 and 1. The dashed red line shows how far away they are from the center line. And even for the added latency case, you can see they're basically saturated in. So what we can observe from this is that there's this of how they're following the path, how are they doing the curves, and this toggling behavior. So we want to try to characterize or capture these characteristics with our human model. And so the question is, can we develop a mathematical model, just a little differential equation basically, that behaves like a human driver? Now in the automotive industry, there's a huge literature on driver models. People use these all the time when they're developing new powertrains and drivetrains. So the standard is to use this look-ahead model, where you assume that the driver is projecting out to some future state and computing what the expected error is, and then doing feedback control on that projected error. So we just wrote this little feedback block diagram, which is pretty standard in the control system. And what we showed is that we could develop for this driver, whether it's a human or this mathematical model we wanted, it's just a PD controller on this projected look-ahead. Now we did tune different PD gains for all the different delays. So people, and this is true in the driver literature as well, that the gains will change depending on the look-ahead distance and any delay that might exist in the system. And so what I want to show you here is, this is the same two paths with the same two delays, but this is not a real human, this is our driver model, our little differential equation. So qualitatively, it looks similar. And now that we have this driver model, we can plug it into the closed loop system, and we can take that same trend line. Here I only showed it for the 1 meter per second, but it looks similar for 1.5 meters per second. And because it's easy to do tests with models versus with real people, we can test that intermediate constant latency, which you see in the open blue boxes, with the variable latency distribution that we have. And you can see that they match fairly closely, right? The reason that the dots don't all land on top of each other is because of that noise that I mentioned that we added to the driver input, just to register the fact that there's not always perfect control of the human into the system. So this is simulation results. And so then we said, okay, well, this looks really good, and this hypothesis is interesting. Let's see what it would look like. And so we went out and we rounded up a bunch more users, and we said that instead of just considering this particular distribution, which is this one, as you can see, it's kind of a one-sided distribution. We pulled this from some earlier work I'd done on wireless networks. So it has a minimum delay, and then you add in the absolute value of a standard normal distribution. We also tested some standard normal distributions that we conjectured, based on their means and standard deviations, would have similar performance to both that equivalent constant latency as well as this distribution of latency. And so this is the results of the next user test. What you can see along the bottom is this 380 was what we conjectured would be the equivalent constant. This is the same distribution we tested before, which you can see up above. This is a normal distribution with mean of 250, standard deviation of 75, and this is a normal distribution with mean of 175 distribution, or variances, we have 118 milliseconds. So in real people, the performance is similar. You can do all the statistical tests and say that, the null hypothesis that these are different is invalid, and so it's impossible to distinguish between these different distributions. So that's really what we're trying to understand now going forward, and we started trying to write out all the mathematical equations. But most of the work, at least that I've seen on network control with stochastic delays, is only focused on stability. I'm trying to understand what's the stability of the closed loop. Here, the closed loop is plenty stable. The magnitude of the delay is not enough to degrade the stability, but we're trying to understand how can we be able to predict the performance in this closed loop with these different distributions and with the different means of variances. So that's the sort of one thing that I'd like to throw out at you. If you guys have any good ideas or have seen something similar in another domain, I would be very interested to see it. These results are actually in our paper. I don't know if it's going to get accepted or not. But wrap up and conclude. So the message I wanted to tell you is that the PD controller with a look ahead can be a good model of user behavior in a teleoperated driving scenario. And we can use this mathematical model to predict the performance for delay distributions that were not tested in practice. And then we can use that to go back and say, yeah, it seems that that hypothesis is valid and is not refuted, let me say, by the test that we did. I'm sure it's not completely proved yet, at least not from a control theoretic point of view. And I'll be happy to tell you that we've managed to convince our sponsors in the Army that direct teleop is not the answer. And we need to look at more adding autonomy and do shared control between the human and robots. So this is really the future direction that we're going with the research in conjunction with the Army. And I know I'm almost out of time, but I have a 2-slide advertisement that I'd like to put up, which is about the robotics group at Michigan. So you might recognize some people that you see here, or you can go to our website and see what we have. Over the last couple of years, we've been developing a big group in robotics, and we've started an initiative. The biggest news, I guess, that we have to announce is that we have a new master's and PhD program in robotics. 8 students enrolled last fall, 5 PhD and 3 masters. We're just going through admissions this year. We connect with the local industry around Robotics Day. Last year we had more than 500 people come to Robotics Day. We expect to have a large group again this year. And we're doing lots of interesting research and connected in autonomous vehicles, as you might imagine, automotive industry, as well as rehabilitation robotics and lots of other different kinds of things. So a lot of people I talk to say, I didn't know Michigan was doing anything in robotics, and so I thought I would tell you all. Thank you very much for listening. I'd be happy to take any questions.
Any questions?
Yes, ask.
So the teleoperation of driving is a really interesting task. And then I was wondering what you're doing with sort of remote teleoperated driven robots, how that might connect to self-driving cars or shared autonomy of someone sitting in the car.
So I'm not personally looking at the shared control within the car. My work is all teleoperated, but I think there is always the question of when do you do the trade-off. And if you have multiple inputs coming in from the person and from the autonomy, how do you know which one to trust? Even with the teleoperated, we might say that you should trust the autonomy, like to not drive into anything, right? Because you might damage your robot. But then you talk to the guys in the Army and they're like, well, maybe I want that robot to bump into that thing and knock it over, right? I mean, so you need to somehow have this way that you can communicate and have this shared experience. And sometimes, yeah, the guy was just being lazy if he didn't want to run into that rock or whatever it was. But sometimes it might be a meaningful input. And so I think those are really hard questions to answer. I don't have the answer, but I think it's an interesting research question.
I think I missed it, but I apologize. But what are the severe scenarios that you would want the car teleoperated? I mean, that would mean that there is nobody in the car.
So what I showed was not a car, it was more of a small ground robot, like in a search and rescue situation, or exploration of a new, so a forward movement in the
Because then you
military.
showed some pictures from real,
Right.
drone scenarios, so I got kind of confused.
Right, now, I don't think we're thinking that this teleoperation scenario would be for a full-scale car.
Okay.